Hello everyone and welcome to today's webinar hosted by the Institution of Mechanical Engineers. On today's webinar we will have a 30-minute presentation looking at function safety and its relation to product safety delivered by David Ward of HORIBA MIRA. Following this, David will be taking any questions that have been submitted throughout the presentation, so if you do have any questions please submit them into the box on the right hand side of your screens. So a little bit about our speaker today. Dr. David Ward is a Senior Technical Manager for Functional Safety at HORIBA MIRA. As many of you will know, HORIBA MIRA is a leading independent provider for automotive engineering services. David Ward is a recognized international expert in automotive functional safety with over 25 years of experience in safety and reliability of embedded electronic systems in automotive and other industries. Within his role at HORIBA MIRA, David is responsible for training, consultancy, and independent safety assessments in functional safety standard ISO 26262 and other related standards. He is involved in automotive cybersecurity as well as the technical development in functional safety, connected and autonomous vehicles and vehicle electrification. David is the UK principal expert for many ISO standards relating to functional safety of road vehicles. He was also part of the working group developing a new standard for cybersecurity engineering. David was presented with the IMechE Prestige Award for Risk Reduction in Mechanical Engineering following 20 years of work leading automotive industry efforts to develop international safety standards. These efforts began with the Motor Industry Software Reliability Association and have continued with the development of the international standard ISO 26262, which Dr. Ward and his team at MIRA continue to influence as they consider how to extend its scope to highly automated vehicles. David is also visiting professor of functional safety at Coventry University, UK, and RAE visiting professor of industrial design at the University of Leicester. Thank you for joining us today, David.
Thank you for that introduction and welcome to this webinar on functional safety and its relation to product safety. To look at the agenda for today's session, I'm first of all going to begin by introducing the terms functional safety and product safety and explain what we understand by those and particularly to briefly explain how functional safety and product safety are addressed in the automotive industry. What I then want to do is to look at how the automotive industry approach to functional safety also includes product safety in its scope. I'll then share a brief case study, make some practical observations and end with some concluding remarks. Although this webinar is focused on an automotive industry view, I believe that many of the principles we'll share today are more widely applicable. So first of all, what do we mean by functional safety? There is a textbook definition which states that functional safety is the part of the overall safety of a system that depends on that system operating correctly in response to its inputs. This is an important definition because it recognises that what we specifically call functional safety is a subset of the overall safety issues associated with a system or a product. And it's particularly concerned with where we use a technology-based system to perform some activities, and if the system does not do those activities as required or as specified, then a potential safety issue may result. Looking across many industries, we find a number of different approaches to functional safety. In some sectors, functional safety is particularly associated with where we deploy a designated safety system to monitor a system for adverse conditions developing and to take some action such as a shutdown system. So a designated system is designed and deployed to reduce the risk associated with a particular hazard. And that's an approach that we find in many industrial contexts. In the automotive industry, and especially in the standard that we use for functional safety, ISO 26262, the specific focus of functional safety is in addressing hazards that can result from malfunctioning behaviour of electronic control systems. And this is a definition and a scope that recognises the fact that the modern road vehicle is highly dependent on its electronic systems and the software embedded in those systems. The electronic systems control many of the safety-related functionalities on the vehicle, such as powertrain, braking and steering, and if the systems misbehave, if the systems malfunction in any way, it could potentially cause a safety issue. One of the important points about the way that functional safety is defined, especially in ISO 26262, is that wider safety issues, of which I'll give some examples shortly, are excluded from the scope of 26262's activities unless they are specifically associated with a malfunction of an electronic system. Nevertheless, I strongly believe that functional safety is to be regarded as a system or indeed a product attribute in the automotive industry. Before I explore that topic in more detail, I should just mention that where on the slide I've highlighted particular terms in blue, those are terms that have a specific meaning or a specific interpretation in the context of safety disciplines. I will not give the formal definitions of those today, but those may be of interest for further reading. I mentioned that I strongly believe that functional safety and indeed wider product safety attributes are core product attributes of vehicle development. I'm showing here a very typical vehicle development life cycle. This is something that's been based on our experience of working on a number of vehicle programs over many years, and we see a common pattern emerging, where first of all in the early stage of the vehicle development program, there are activities around setting the targets for the vehicle, benchmarking comparable products and setting product targets and product attributes. Those are the activities which are contained in the first two elements of the life cycle, which are shown to the left there. So in traditional vehicle engineering, it's very common to set product attributes both in terms of objective attributes, such as range in electric vehicle mode, such as acceleration. We also set subjective attributes such as ride and handling, noise, vibration and harshness. Those are set as early attributes in the program definition so that we can then go ahead and design and implement a product that meets those attributes. I strongly encourage that people view more technical subjects such as functional safety in the similar way. Within the standard ISO 26262, we have an activity called the concept phase, where in the concept phase we carry out a hazard analysis and risk assessment to identify in conceptual terms how the electronic product that we want to develop could malfunction, and as a result what safety requirements we set on that product. In technical terms, in ISO 26262, the high-level requirements are called safety goals, and there's also an attribute called ASIL, or Automotive Safety Integrity Level, associated with the safety goals that is a measure of the robustness that is required in the design and implementation. Those are also to be seen as product attributes and ultimately as safety attributes of the vehicle. The other important aspect I'd like to draw attention to in this life cycle is that towards the end of the product development activities, there are stages where we approve the vehicle for volume production and ultimately for sale. You'll notice that at the top of this image there is a milestone or gateway called engineering sign-off, and after that activity we proceed to something called certification and homologation. That's the point at which we establish that the vehicle is suitable for release and to ensure that it meets the relevant legislation that applies to the vehicle. I'll be saying more about that shortly. Moving on to consider product safety. Product safety is a more wide-ranging area. It's more wide-reaching. It's concerned with all safety aspects of a product. And when we refer to product safety, we're usually understanding that to mean a consumer product. Product safety is covered by various aspects of legislation. In particular, there is a general product safety directive under which a product is considered safe if it meets all statutory safety requirements as set out in European or national law. There is quite a long definition of what constitutes a safe product. You may search for this directive and read the text yourselves, but I would like to just draw attention to some key points from this definition, which is that a safe product includes a product which under normal or reasonably foreseeable conditions of use does not present a risk to users of the product, to where that risk is considered to be acceptable and consistent with a high level of protection for the safety and health of persons. Where there are no specific regulations or standards that apply to aspects of product safety, then compliance is determined according to other reference documents such as national standards, recommendations or codes of practice. So we may see that functional safety is a subset ultimately of product safety. We also find occasionally that people talk about system safety, so we may see system safety as being concerned with the safe behaviour of systems, whereas particularly in the automotive industry, functional safety is specifically concerned with safety issues that result from malfunction. So a key point that I'll be coming back to later in this presentation is that increasingly we recognise that functional safety in automotive, particularly as covered by ISO 26262, is a subset of system safety, where we're concerned with the correct and safe functionality of a product, not just its behaviour in the presence of malfunctions, and ultimately that is also a subset of product safety. So more precisely, what do we mean by functional safety in the context of 26262, and how might this be related to product safety? There's a very specific definition in 26262 that safety is defined as absence of unreasonable risk. Many approaches to safety, including the General Product Safety Directive, are based on an approach where we evaluate the risk associated with a product, and if that risk is not judged to be at a level that's considered acceptable, then we need to take measures to reduce that risk. Within 26262, the term unreasonable risk is used, and one possible source of this is motor vehicle safety legislation in the USA, which establishes the principle that the public is protected against unreasonable risk of accidents occurring as a result of the design, construction and performance of motor vehicles. So clearly the global framework for motor vehicle safety is concerned with product safety, and this is addressed through vehicle legislative requirements such as in the US, the Federal Motor Vehicle Safety Standards, and in other parts of the world within Europe and other parts of the world through whole vehicle type approval regulations. So looking at how product safety regulations are applied in the automotive industry, every nation or every area of the world where vehicles are sold or put into use will have its own approaches to vehicle regulations. Many of these adopt the national or international regulations, such as the worldwide type approval regulations, but there may also be some local approaches that apply as well. So, for example, in the UK, we apply the whole vehicle type approval process, but we also have the construction and use regulations, which are our specific UK approaches. Many of these legislative approaches are concerned with product safety, but often these set minimum requirements. There's an assumption that a vehicle manufacturer will be following an engineering process, and often the regulatory approaches are a check that an appropriate and thorough approach is being followed. But often driven by general product safety concerns and also by considerations of product liability, manufacturers will often go beyond those minimum requirements that are set in legislation. The other factor which exists in the automotive industry is our approach to quality management. This is found in a document called IATF 16949, which is essentially an automotive industry interpretation and extension of ISO 9001. This is often used as the framework to set quality management and process control requirements, for example, between a vehicle manufacturer and a supplier. But this document does contain a set of specific requirements on product safety. Turning back to the subject of functional safety and ISO 26262, we've already noted that the scope of that standard is quite narrow compared to wider product safety. So does 26262 have anything to say about product safety, and how might we see the relationship between the specific activities of functional safety and the wider product safety activities? The scope of 26262 is deliberately narrow because we specifically created a standard that ultimately is concerned with the design and implementation of safety-related electronic systems and the hardware and software within them. So we did not set out to create a product safety standard, recognising that the wider aspects of product safety are already addressed through other standards. So the scope statements within ISO 26262 exclude functional performance aspects of a system, and they also exclude certain hazards. So it's a non-comprehensive list, but topics such as electric shock, fire, smoke, heat, radiation, etc. are what we often call specific hazards or particular hazards associated with the technology. In the case of a traction battery that's used in an electric vehicle, for example, there are hazards associated with potential exposure to hazardous levels of electrical energy. That is a wider product safety issue. There are other standards and regulations that deal with aspects of that. It only comes into scope of ISO 26262 if we are using an electronic system to monitor the performance of the battery and to control the performance of the battery in such a way that we avoid those events happening. We also find within ISO 26262 that the definitions that are used of harm and hazard are quite specific. A hazard refers to an unwanted vehicle state caused by malfunctioning behaviour of an electronic system that has the potential to cause harm, and harm is concerned with physical injury or damage to the health of persons. It does not include wider impacts such as economic or environmental impacts. So just to give some examples, relevant product safety regulations for an electric vehicle include the specific regulation concerned with electrical safety. There are also regulations concerned with crashworthiness. Those talk about both the physical protection of occupants in the vehicle. They also cover electrical safety in the event of a crash and what happens during rescue and recovery after a crash. So does that mean that ISO 26262 ignores product safety? Very resounding answer to that, no. ISO 26262 is concerned with product safety, but it recognises that functional safety is a specific subset of that, concerned with malfunctioning behaviour of electronic systems. There's an introductory remark within 26262 that the processes that it contains can provide a framework within which safety-related systems based on other technologies can be considered. So it would be possible, if there is another technology-based issue that we need to deal with, that we could take some of the principles of 26262, particularly principles of hazard analysis and risk reduction, and adapt them appropriately for other activities. Although the core scope of 26262 is concerned with how those requirements feed through into electronic systems. Secondly, ISO 26262 also acknowledges that in many cases the implementation of the systems, particularly around electronic hardware and software, will use common development processes. There's a slightly mysterious turn of phrase. Safety is referred to as being intertwined in other product development activities, and there's explicit acknowledgement, for example, in the way that we develop software, that a software development process will have to consider sources of requirements from other sources beyond 26262 and integrate those and align them with the 26262 process. So 26262, although focused on the electronic systems, does acknowledge that its activities cannot be viewed in isolation to other product safety activities. A further question is how we deal with hazards that are out of scope. In our hazard analysis, if we identify something that is not in scope of 26262, we are not permitted to to overlook that. There's an explicit requirement that the means to address that hazard, to reduce its risk, are communicated to the relevant parts of the organisation developing the product through the appropriate procedures. And also, in the latest edition of the standard, we've introduced a new requirement to institute and maintain effective communication channels with other disciplines that may impact on functional safety. Originally, this was introduced by motivations concerned with cyber security, but other examples that are given here include mechanical engineering and quality management. So it's recognised that the functional safety activities cannot be viewed in isolation from wider product quality and product safety issues. And it's notable that where this requirement is given is actually in the requirements to establish and maintain a safety culture as part of the overall corporate safety management in an organisation. Despite the narrow scope of 26262, it is now being acknowledged that there are wider system safety and product safety implications that have to be considered. One area where the industry is putting quite a lot of effort at the moment is concerned with the functional performance or nominal performance of driver assist and higher levels of automation functions in vehicles. And we're addressing that through a new set of requirements that are emerging under the title of Safety of the Intended Functionality, or SOTIF. I will not go through the details of the table that's shown on this slide, but this is just to recognise that it's now acknowledged in the scope of the work we're doing to develop the SOTIF requirements that the classical malfunctions that are addressed in ISO 26262 are one of only about 10 factors that address the overall product safety. So we see that wider activities such as cyber security, safety of the intended functionality, interaction with the environment and other systems, and even the human-machine interface are also important topics that have to be considered. So pulling all this together, the functional safety approach that's found in ISO 26262 is very much seen as a subset of system safety and ultimately of product safety, as I explained earlier in the presentation. It's worth noting at the same time that approaches that are emerging for cybersecurity in the automotive industry are seen as having significant overlaps with the functional safety activities in some cases. Moving on to consider system safety, the work that's going on to address safety of the intended functionality is a good example of how the automotive industry is addressing wider system safety issues. So how do we address and assess safe functional performance of a product in the absence of malfunctions? And ultimately, this is in the context of wider product safety as defined through the requirements of something like IATF 16949 and the legislative requirements in activities such as type approval. So let me now share a brief case study. The example I'd like to look at is the example of an electronic steering column lock. This is an electronic system that is found in many vehicles that have keyless start, and it replaces the physical ignition key lock, and it's deployed in vehicles as a security measure. When we approach this from a functional safety perspective, the potential failure modes that we would identify and the hazards that would result are things such as undemanded locking. So while the driver is driving the vehicle, potentially a malfunction could cause the steering column lock to deploy without valid conditions being met. Secondly, a malfunction could be that the system fails to lock the steering column after the driver has parked the vehicle. Usually from a functional safety perspective, that's not considered safety relevant. It will not lead to harm to a person, but it is still considered a significant characteristic of the vehicle because potentially it could lead to a failure to meet legislation. And another potential failure mode is failure to unlock. So before driving away from a park position, the driver starts the vehicle, but the steering column lock hasn't unlocked. As we do the hazard analysis, we assign safety goals and ASIL values to these, and then as we start the system design and implementation, we start to explore the design solutions for the causes of these potential failures. And when we're addressing undemanded locking, for the most part, the causes that we'll be interested in are electronic system malfunction. So the scope of addressing that potential hazard is fairly and squarely within the scope and context of ISO 26262. However, when we look at failure to unlock, clearly an electronic system malfunction could be a cause of that, but it could also be caused by a mechanical failure or a physical factor. So it could be caused by simply the position of the steering wheel, meaning that the bolt doesn't release, or it could be a physical factor such as a low temperature, or perhaps a manufacturing defect that's introduced some contamination into the locking mechanism. Clearly those latter two causes are out of scope of 26262, but they would still need to be considered as causes in the functional safety design of an electronic system, because we may, for example, wish to deploy a strategy that warns the driver that steering column lock hasn't released. And I've seen this in real life in vehicles where there's a message displayed that asks the driver to turn the steering column to unlock the column. It may also be that the strategy then is to discourage or prevent use of the vehicle if the steering column remains in that lock condition. So this is a very good example of something that has a mechanical or wider product safety root cause, which there may be a risk of people overlooking if they focus on the very narrow interpretation of ISO 26262. So it's very important in this case to consider the interactions with, in this particular example, mechanical engineering. So to make some practical observations, the new requirement that's in ISO 26262 to consider the links and interactions with other disciplines is very important, and I strongly recommend that people performing functional safety activities do take note of those requirements, and equally so that people working in other disciplines in wider system safety and product safety are also aware of the implications and approaches being used to functional safety. In the latest version of ISO 26262, secondly, we now have the possibility to consider an objective-oriented approach as we deal with novel or different technologies. That there's now a route to demonstrate that the requirements and objectives of the standard have been met, perhaps through alternative solutions or different approaches to those ones that are listed in the standard. And again, that gives us the flexibility to adapt good practice from 26262 to deal with novel challenges and new technologies in vehicles. Very significantly, many of the existing approaches and activities that we use for product safety, quality, reliability, particularly around things such as failure mode and effects analysis and design verification plans, are of course already wider product safety activities, and the specific activities that we need for functional safety should leverage and extend these. One of the most frequently asked questions I get about functional safety, particularly from traditional automotive engineers, is where does something like FMEA fit into this? And we can build on and extend the existing approaches to meet the needs of functional safety. We should not be trying to set up a completely different set of analysis and verification processes, but rather looking to enhance and augment them to meet the needs of functional safety activities. And it's also worth remarking that quality requirements such as IATF 16949 may again set baseline processes for product safety and product quality, which can make a significant contribution to achieving the requirements of functional safety activities. Another important approach that's emerging in the industry is the use of a safety case, and in particular the use of an argument-based safety case for electronic systems. The requirement for a safety case has always existed in ISO 26262, but it's now specifically required to be based on an argument approach, and indeed in the UK automotive industry, the MISRA consortium has recently released guidelines on how to construct an argument-based safety case in support of ISO 26262. but a safety case can be extended to cover wider aspects of product safety beyond just functional safety, and the safety case can also be expanded to cover wider aspects of product assurance, such as cyber security. So the industry has at its disposal a number of methods and tools that allow us to achieve product safety, system safety and functional safety, and to provide the evidence and the argument for how those have been achieved. So to conclude, within this session, I've demonstrated that product safety in the automotive industry is a core product attribute. It's embodied in legislative requirements, and it's embodied in industry practices which build on and go beyond those legislative baselines. And in particular, because the modern vehicle is highly dependent on its electronic systems and the software in those systems, functional safety is a specific aspect of product safety that has taken on great significance over the past few years in the automotive industry. Even though 26262 has a deliberately narrow scope, it does implicitly acknowledge product safety throughout its structure and requirements. And 26262 should therefore be seen as a framework for addressing functional safety in the context of wider system safety and ultimately product safety. And therefore, users of standards and industry approaches such as 26262 should be seeking synergies and commonalities in their existing activities and their wider processes. Thank you for listening, and I'm now happy to take questions and discussion.
Okay, good afternoon everyone. It's David Ward here. Thanks for taking the time to listen in to the presentation. So had a number of questions come in already, which is great. There's some really good questions. So I'm going to start by working through the questions that I have already, and if anyone thinks of anything else whilst I'm answering those, then please feel free to respond to those. So I'll start with a question that's come in saying, how closely does 26262 fit or tie in with other standards? 61508 and 61511 were specifically mentioned. So the intention in developing 26262 was for it to be the product and sector specific version of 61508, and certainly we wanted to have it. There was a stated intent that it should be seen as having comparable status to 61508. So if I comment on that first of all, the idea was that it should be seen as the state of the art. It should be seen as the go-to standard in the industry and have a comparable standing to 61508, and that's certainly been very much been the outcome. In terms of how it relates to 61508, although many of the concepts and principles are broadly similar, so it's a safety life cycle driven by the concept of risk reduction. It uses safety integrity levels and so on. There are some details in the way that 26262 is implemented that make it quite different from 61508. So although it's very much coming at functional safety from a similar perspective, some of the approaches are quite different. So things like the safety integrity level that's used in 61508 and the ASIL that's used in 26262 are not directly equivalent. And also the definition of harm in 61508, for example, is broader than 26262. So within 61508 it can cover environmental damage and financial loss as well. So probably the scope of 61508 is a bit broader in that respect. So that's the first question. The second question I've had, and there's actually I think two questions that probably go together. One is saying how's the reliability addressed with regard to product safety, particularly once the product's released. In other words, how can the product be maintained with reliability in mind? And also there's a question that's asking how to ensure the functional safety of the product is sustainable and applicable throughout the product's life. So both of those are addressed in 26262. To kind of take the first question first of all, there's a baseline assumption that a company is already following baseline quality reliability engineering practices. So those are there as a given, and 26262 is seeking to build on those. Once the product's released, then 26262 does have activities around planning for continuing the support of functional safety post-release of the product. So things like things that might occur during operation, during maintenance, and at the end of the life of the vehicle are things that are covered. I think one of the specific challenges that we face is how we'd address how we address the long lifetime of the vehicle. We don't necessarily have the kind of same preventative maintenance regime that we have in other industries. So one of the factors that we have to take into account is addressing through life safety and making sure that if systems have later in life failures, that those are managed in a safe way, taking into account the fact that later in life owners may not have the same sort of level of rigour in maintenance as they perhaps do whilst the vehicle's under warranty. So thanks for those questions. The next question I got is whether you'd see a baseline functional safety assessment carried out during the concept phase. Absolutely yes. Although in the slide I showed functional safety assessment at the end of the life cycle, that's talking about completion of the functional safety assessment, and the reality is that we'd expect that those activities are actually ongoing during the safety life cycle. Within 26262, functional safety assessment is part of something called the confirmation measures, which is a set of independent review activities, and certainly the concept phase activities, particularly the hazard analysis and risk assessment, is something which is subject to a specific confirmation review. So there is an expectation that at least the results of the hazard analysis have an early phase assessment carried on out on them. There's also a question about ultimately who decides what is a reasonable or unreasonable risk, and ultimately that's going to be for society to decide. So I think there's a tendency that engineers think that that's their decision to make, but ultimately it'll be society that judges, particularly if there's any kind of regulatory or similar investigation that takes place. So I'm just reviewing some of the other questions here. So there's a question that's come in saying, could you let us know if the product's compliant with 26262, how we can quantify the safety improvement? So I think as I understand this, we see quite a lot of activities in the supply chain, which where suppliers, particularly tier 1, tier 2 suppliers, are coming forward saying that they have products which comply with the requirements of the standard. I think it's very important to recognise that when you're talking about a lower level element in the system, that's talking about a capability, and whenever anyone comes forward with a product like that, say a microcontroller or an operating system or even a complete ECU, you always have to quantify what it's going to be used for and how the capability of that element fulfills the safety requirements in the context that it's used. So I think one aspect of answering that question is that we should we should always see an off-the-shelf product as having a capability, and saying how does it integrate into the context in which we use it. The other important aspect is that we should have products under continuous review, continuous improvement. Just because we developed it according to the standard, it was shown fit for purpose at one point in time, particularly where we're dealing with some of the lower level elements, then we'd expect to be continuing and continuous improvement. We've got another question about other standards. Someone was saying, are there other standards that are similar to 26262 for other industries? Yes, there are. 61508 is the standard which is globally applicable, and many sectors have their own sector-specific interpretations of that. There's also similar but developed in a slightly different way standards in aerospace and defence, etc. So we've got another interesting question where someone's asking about the expectations for Tier 2 material suppliers. They're talking about manufacturing a particular type of material for lithium-ion batteries, and they can share with their buyers the conditions that may result in a thermal runaway. Is that enough to be certified for 26262? I think the first thing to say, first of all, is that 26262 is the certification standard per se. There's no explicit requirement in the standard to get any form of product certification. In fact, what the standard requires is independent assessment, which some of the suppliers may choose to do with an external body who may offer a certificate, but those certificates are commercial propositions of certification bodies rather than an explicit requirement of the standard. I think when we come to things like material supply, it's not meaningful to put a 26262 requirement directly onto the material supply per se, but this is actually an excellent example of where we should look at the interactions between functional safety and product safety, because ultimately preventing something like thermal runaway in a battery pack is a product safety issue. There'll be wider aspects that need to be considered, and certainly I would see that yes, there might be specific constraints or controls that come out of the functional safety activities, but I'd expect them to be addressed through standard supplier relations and quality processes. So I wouldn't expect to see necessarily an explicit 26262 requirement at the level of material supply. So some other questions that have come in. Someone's asking, how are functional safety checks carried out and recorded? Are they a study of a group of people involved in the project, or a tick box or check sheet? What is the stance on common designs or systems, and are checks needed each time, or once it's been completed, does this cover future similar designs? So I think that's continuing some of the themes that we've seen already. So certainly one of the things that the standard is strong on is recording the evidence and also the argument for why we've done functional safety activities and why the ones that we've conducted are appropriate. That's where the requirement for a safety case comes in, and also where the requirement for independent reviews come in. Generally speaking, I think that should involve more than just a tick box or check box. We see quite a lot of people trying to have a checkbox mentality to following the standard, but ultimately something like a functional safety assessment does involve making a judgment on the level of functional safety that's been achieved. And I think that yes, once a lower level element like a microcontroller or something that's going to be incorporated into a product has been developed, then certainly then yes, with appropriate evidence, it's possible for that to be reused in other contexts, in other applications. But it's always important that we evaluate what's different about the new context and new application. So generally speaking, reuse is seen as a good thing. Reuse of a proven design, a proven element is seen as a good thing, but we always have to check the context and the application. Conversely, we do see that many people think just because I buy an off-the-shelf product that claims to have an ASIL capability, that's all I need to do for my product design. It's a great start, but you as the integrator or the procurer of that element always have to check the context and the claim capability against your requirement. So someone's asked what I think is possibly a slightly politically loaded question, but I'm going to answer it anyway. Someone said that the slides show the different regulations around the world show the UK and Europe in the same orange colour. Is that going to change to negatively impact functional safety if when Brexit happens? Suggest you direct that question to number 10 Downing Street, but because none of us really know. But I think speaking more seriously, the 26262 is an international standard. It's the common approach that we use in the automotive industry, and that won't be affected by any future shape of Brexit or lack of Brexit, whatever happens. Perhaps one thing we do need to be aware of is that obviously potentially there may be changes in vehicle regulations, but although there's been quite a lot of comments that if the UK is out of Europe, then we're out of the European whole vehicle type approval system. Don't forget, of course, that there's also a parallel world type approval system. So yes, there may be some issues, but I think it's things that can be that can be worked through. I've got another question which is asking about how do the different ASIL levels impact on product test and verification requirements during the production process. So generally speaking, we should understand the ASIL as being a measure of the robustness that's required in the product development. So for higher ASIL values at ASIL D, for example, then we expect more rigour to be followed. Generally speaking, I'd say if we're looking at the production process, and I think this is potentially coming from someone looking at the semiconductor industry, I wouldn't see necessarily that it would affect the production process per se, but it might mean if for example, there's some kind of post-layout or post-silicon test and verification activities, then at higher ASILs you would expect greater rigour of the test methods that are used, greater test coverage, better arguments that would, for the results and the coverage of the tests. We've got a couple of questions now about software development. There's one asking how software development practices such as test-driven development and regression testing fit into functional safety. And there's also another question which is asking whether I could elaborate a bit more on the software functional safety regarding 26262. The hardware, it's more easy to understand, but for software, it's a bit vague. I kind of take issue with that. I think, in the software part of the standard, the approach to functional safety is through having a life cycle where we achieve a certain level of rigour through, as indicated by the ASIL value, so the types of design methods we use in the software, the types of rigour in verification and testing we use increase with the ASIL value, and those are well-established practices. Something like test-driven development is foreseen in 26262. In fact, in the latest edition of the standard, we've added an explicit comment saying that if you look at the standard, it's based on the traditional V model, but we've added a comment that other development approaches like test-driven development can be included. They're seen as what's called tailoring in the context of the standard, which is where we take the base requirements of the standard and adapt them into our own development process. So things like that can be used. The important thing is that they should be seen as a project delivery method. They're not a means to they're not a means to say, oh, it was too hard or we ran out of time to do these functional safety activities. And in my experience, think methods like that used correctly can actually be beneficial to functional safety. Another question we've had is how applicable is the current revision of 26262 to vehicles with higher levels of automation? I would say it is applicable. Clearly, one of the things that we have to bear in mind is that 26262 was developed against the background of assuming there's a driver in the vehicle. So some of the concepts in the standard at first sight don't necessarily translate across to higher levels of automation. So one of the things we have to do is to decide how to adapt the approach in 26262. We've seen people suggesting that we need a completely different approach. Personally, I don't think that's correct. I think we need to build on and extend 26262 for dealing with that type of technology. There are activities underway. One of the key activities is, it's mentioned on one of the slides, is something called safety of the intended functionality. So that's starting to address more of the issues around high levels of automation, and I think whilst that's looking more at the wanted performance, so how well do sensors discriminate between different types of objects, how correct is the functional performance of an automation or driver assist system, I think we do recognise that there's further work to do to build on the foundation of 26262 and look at how it's adapted for high levels of automation, and indeed that's something that that's something that certainly we're directly active on ourselves with some of the work work we're doing with customers. There's a question that perhaps is related to that, saying how does an objective-oriented approach work for autonomy where the vehicle may be learning? Again, I think that's something that's still under development. I think the objective-oriented approach does allow us to look at alternative solutions that fulfil the objectives of the standard, but it's very much something that we're actively looking at the moment. What will be the right way to assure autonomy? Got another good question here which says, with respect to vehicles with high voltage, does 26262 cover requirements for interlocking to prevent user access, and in the event of a crash, what level of isolation or shut-off is required for the HV power system or commodity to enable the vehicle to remain drivable? So short answer is that 26262 doesn't directly cover requirements for things like interlocking and isolation. Those are covered in other standards, for example ISO 6469, and there's also one of the regulations, type approval regulations, Reg 100, that covers that. However, if an electronic system is involved in the interlocking or in a shutdown function or isolation monitoring, then it comes in scope of functional safety. Similarly, crash regulations, Regs 94 and 95, have certain requirements about protection from HV during and after impact. So again, Reg 94, 95, 100 will be seen as product safety regulations that may impact the functional safety design. I think generally speaking, the view is that after an impact that would lead to the need to isolate the HV supply, the vehicle wouldn't be drivable because the safe condition is to shut off and isolate the power supply. There's another question that's come in whilst I've been answering the question, saying, do all aspects of 26262 that you've stated apply to off-road applications? And it's mentioned ISO 13849. So 13849 is used in the context of machinery safety and is quite often applied to off-road applications. That standard has quite a different approach. Perhaps one of the interesting things is that 13849 starts from is often applied where people use designated architectures, and essentially that's a simplified means of complying with the requirements of that standard. In the case you're using a number of off-the-shelf elements and composing them according to a designated architecture. But if you're the person that's actually designing a fairly complex controller as part of that, then the presumption of 13849 would be that you would use 61508 or something like it for the design of the hardware and software within something like a programmable logic controller. So I can see that 13849 might be applicable at a higher level, but we might take some of the good practice from 26262 and apply it at lower levels of design. And in fact, one of the things that we addressed in edition 2 of the standard was, particularly in truck and bus applications, which we brought into the scope of the standard, you may well be faced with a situation where you have to manage that kind of interface to and from a non-26262 application. There's another great question come in that said, how do you address the risk of unknown input? For example, if you allow connectivity via mobile device and app, how can you proof against future software updates of the mobile platform? I would see that probably some of that's coming into the aspects of cyber security, where we would have to think about how the system is protected from external intrusion and external effects like that. And in fact, if you look at slide 11, where I've talked about the number of different factors that can affect the robustness or resilience of the electronic system, that kind of interaction with external infrastructure, with off-board applications would certainly be seen within scope of that. Just reviewing some of the other questions. I think I've answered most of the questions. There's a couple more to address. Someone's asked, are functional safety and product safety engineers co-located in automotive industry teams? I suspect the answer is in reality they're not, but one of the things that we do seek to do is to encourage those interactions. I think a lot will depend on the individual organisational structure within a company, but I guess one of the key messages I've been trying to get across in this presentation is that perhaps we see a tendency in some quarters for people to have a bit of a silo mentality, and we would encourage that at least those interactions take place, and again that's something which is acknowledged in edition 2 of the standard. And as I think I remarked on one of the slides, what's interesting is that the requirement to have that interaction is not contained in safety planning for a specific project. It's actually contained in the requirements to establish and maintain a safety culture. So our intent is that kind of interaction should be embedded deep within the values and culture that's prevalent within an organisation. So just looking over the other questions. Yeah, there's a really good one which I've not addressed yet, which says unreasonable risk is very subjective. Is there a way to demonstrate that risk is as low as reasonably practical, e.g. a grossly disproportionate factor? That's a really great question, and I've got sort of a two-part answer to that. The first is to say that within 26262 itself, we didn't embody the concept of as low as reasonably practical, and I think there was an unwritten assumption that we didn't want to have an explicit calibration in the standard of what does or doesn't constitute unreasonable risk, but essentially the argument would be that if you follow the requirements of the standard, you're following the agreed industry approach, the state of the art, to demonstrate freedom from unreasonable risk, and we didn't sort of want to, we wanted to tie it into demonstrating that that's been achieved through engineering activities. However, the concept of things like a LARP has come back, particularly when we're considering safety of the intended functionality, because there are, as we look at all the different scenarios and situations that a highly automated function might encounter, there'll always be scenarios that we don't know about them and that are potentially unsafe, and so there's going to be an argument, there's going to be a need for an argument made that what we've done in developing and verifying and validating the system is at least as good and preferably better to what's gone before. So things like an LARP argument may well come into that. We are approaching the end of our session now. There is one question that's come in that I haven't addressed yet. I feel that that's probably a little bit technical, and also I perhaps need a little bit more information. So I'm going to take that one. It's talking about DB and BA topics in software. So I'll take that one offline and follow up directly with the question on that. I think otherwise I've probably covered all of the questions that have been asked, unless anyone's got a sort of last minute question. There's one or two questions about availability of the presentation and so on, which I'll leave to IMechE to answer that one. Probably it's approaching the point to thank you all for coming along today, for listening, and for some great questions from the audience. And my contact details are shown on the screen there. If anyone wants to follow up with me individually, then also I'm happy to take other questions offline. So there's perhaps just time for one more question if anyone's got one. Otherwise, I'll hand back to the IMechE staff to do the formal closing of the session. There's time for one final question if anyone has one. Okay, so let's just do. So I don't think there's any further questions coming forward. So once again, I'd like to thank you all for attending. Thanks for making the time to listen to this presentation. Thanks for some really great and insightful questions from the audience. I understand that there will be an on-demand version of this available soon if you want to look over it again or follow up on it. So this is David Ward on behalf of HORIBA MIRA and on behalf of IMechE. Thanks for participating in this webinar on functional safety and product safety, and hope to speak to you again sometime in the future. Thanks everyone.